welcome to another video in our geometry series, and this time we are looking at the measurement of area. By the end of this video, you should be able to do two things. One, you should be able to calculate the area of squares and rectangles, and two, you should be able to find out the possible side lengths for a rectangle with a given area. If you can already do those two things confidently, you might want to skip ahead to a next video. But if you'd like to go deeper with your understanding of those two skills, jump in with me and we can work on it together. So, to begin with, what is area? When we measure area, what is it that we are measuring? Well, last time in our video on perimeter, we talked about the idea of dimensions, and we mentioned that in that video we were measuring in one dimension. We were measuring length, and we introduced units of measure for length, one of which would be centimeters. Another might be meters or kilometers. In each case, we are measuring in one dimension, we are measuring length. Well, now we are going to add another dimension. So in addition to length, we are going to be looking at the idea of width. So now we are measuring in not one, but two dimensions. So how do we do that? What kind of units can we use to measure in two dimensions? So we're not going to be using centimeters or meters or kilometers. We're going to be using something called square units, because in this case we are measuring how much space is filled in two dimensions. We're measuring the inside of a shape. So for example, here is a square unit. This is a square centimeter. Now, we call them square units because when we go from one dimension of length and add a second dimension of width, we end up creating a square. So here is our length dimension. And now we've added that second dimension of width. And these two dimensions give us a square unit, because we're using the same side length measure on each side. So because both sides are a centimeter, both dimensions measure 1 centimeter in extension, it gives us a 1 centimeter square. And the symbol that we use to indicate that we are dealing with a square centimeter is cm2. This little 2 means we are now measuring in two dimensions. It would be the same if we were doing square meters or square kilometers. In each case, we add this little 2 to show that we're dealing with square kilometers and not kilometers just in one dimension of length, for example. Here are a whole bunch of square centimeters. There are 12 of them, to be exact. So I could say that right now I have 12 square centimeters. So here I have 3 rectangles. Each of them has different dimensions. Their sides and lengths are all different. But I'll tell you right now, each of them has a measure of 12 square centimeters. That means that the inside space of each of these is the same, and I can prove it to you like this. I can move these 12 square centimeters so that they fit inside this one rectangle. And as you can see, I'm going quickly, but I'm going to do my best to be careful. And when I'm done, you'll see that the inside space here is equal to these 12 square centimeters. And I can also show you the dimensions of this rectangle. It is 1 centimeter in width, and it is 12 centimeters in length, and inside of it, as I said before, we can fit 12 square centimeters. Let's look at another rectangle. Let's look at this one right here. Now again, I'm telling you now, it has a measurement of 12 square centimeters, and to show you, I'm going to put these same 12 square centimeters inside this rectangle. And again, I'm going kind of quickly, but I think you can see as I finish up here that the inside space is equal to 12 square centimeters. Now, let's reveal its dimensions. On this side width, we have 3 centimeters. 1, 2, 3. And on this length, I have 4 centimeters to make a total of 12 square centimeters inside. Let's do one more. I'm going to move this over to free up my square centimeters again. And let's look at this rectangle. And again, I'm going to promise you that it as well is equal to 12 square centimeters. Let's see if I'm right as I move these 12 inside this rectangle. And as you can see as I finish up here, in fact, it does have an inside space that is the same as 12 square centimeters. And let's look at its dimensions. It has a length here of 1, 2, 3, 4, 5, 6 centimeters, and a width here of 1, 2 centimeters, giving it again an area of 12 square centimeters. Each of those rectangles had the same inside measurement. Each was 12 square centimeters. Each was different, but they all had the same inside measurement. So that makes me wonder, is there a formula that we can come up with that calculates the inside area of squares and rectangles? Now, you may have noticed something. The first rectangle we looked at had dimensions of 1 centimeter in width and 12 in length, and had an area of 12 square centimeters. The second had a width of 2 centimeters and a length of 6, and had an area of 12 square centimeters. And the third had a width of 3 centimeters and a length of 4, giving it an area of 12 square centimeters. Can you see a connection between the side lengths and the widths and the areas of each of those rectangles? Well, I bet you can. I bet you've already noticed that 1 times 12 equals 12, that 6 times 2 equals 12, and that 3 times 4 equals 12. And if you didn't notice it before, I bet you can see it now. What we have here is a formula that can tell us the area of any rectangle or any square. And remember, a square is just a specific kind of rectangle. The formula that we can use is length times width equals the area. For any rectangle, if you know the length and you know the width, you can find out the area. We're multiplying one dimension, the length, by the second dimension, the width. Let's look at a couple together. So here is a rectangle that has a length of 7 centimeters and a width of 3 centimeters. Well, we know our formula is length times width equals area. So what's the length? The length is 7 centimeters. The width is 3 centimeters. And we all know that that would give us an answer of 21, which means that the area is 21 centimeters, but what kind of centimeters? We're looking at square centimeters. So we write that like so, 21 square centimeters. That's what that 2 means. It means we're measuring in 2 dimensions. So, square centimeters. Let's look at another one here. Here we have a second rectangle. Its length is 12 centimeters, its width is 9. And again, our formula is length times width. So, let's do the math. We have 9 times 12, which gives us a measure of 108 centimeters squared. We're measuring in 2 dimensions, so our area is 108 centimeters squared. The inside space that this rectangle takes up, or the space in 2 dimensions that we're measuring here, is 108 centimeters squared. Let's look at one last one. Here we have a rectangle. Again, it has its dimensions identified here. Its width is 2 centimeters, its length is 20. Our formula again is length times the width equals the area. So let's do that. So we have 20 times 2, which gives us 40 centimeters squared as our answer. Okay, so the area equals 40 centimeters squared. Length times width equals area. Measuring in 2 dimensions. So, if we go back to the beginning of our video, we've now just covered this first part. We can calculate the area of squares and rectangles by using the formula length times width equals the area. But our second question was this: how can we find the possible side lengths of a rectangle with a given area? If you had a rectangle and you knew that its area was, for example, let's say 28 centimeters squared, what could its lengths and its widths be? And in fact, there might be more than one rectangle that could give us an area of 28 centimeters. What might all of those rectangles be? Well, let's look at that next. Let's go back over here and think about this for a moment. So here is a rectangle, or several rectangles, and we know that it has an area of 36 centimeters squared. Remember, at the beginning, we worked with rectangles that all had an area of 12 centimeters squared. So you could have multiple rectangles with the same area, even though their outside measures are the same. Their perimeters are different, but their areas could be the same. So let's think about this before. Do we have a strategy that we could use to figure out the different possible dimensions of a rectangle that has an area of 36 centimeters squared? Okay, we know that the formula is length times width. So I know that I'm trying to find all of the factors of 36, the numbers that when multiplied together will give me 36 as an answer. So I always suggest starting with the smallest and largest factors to make sure that I can find them all. So if I started with the smallest number I could, does 1 go into 36? Yes. How many times? Well, 1 goes into 36 times. Can 2 go into 36? Well, I know it can because 36 is an even number. And 2 times 18 is 36. Can 3 go into 36? Well, if I do the math, I can find out that yes, in fact, it does. 3 times 12 is 36. If I remember my times tables, I can get that one. Can 4 go into 36? Well, I know it does. 4 times 9 is 36. Notice that my numbers are getting closer and closer together here. Is there any other number after 4 that goes into 36? 5 doesn't, I know that. Can 6 go into 36? Well, I know it does. 6 times 6 is 36. And once these numbers are the same, or once I know that there's no other number in between these two numbers, I know I've found them all. So here are all of the possible side lengths of a rectangle that has an area of 36 square centimeters. Let's try another one. Someone says to me, I know of a rectangle that has an area of 40 square centimeters. In fact, I bet there are several. What could their side lengths be? Well, let's use that same strategy. I know that one of its side lengths could be 1 centimeter. 1 times 40 is 40. Well, does 2 go into 40? Yes, it does. 2 times 20 is 40. Does 3 go into 40? Well, I know my 3 times tables, and I know it doesn't. Does 4? Yeah, 4 times 10 is 40. Does 5 go into 40? Well, I know that every multiple of 5 ends in either a 5 or a 0. 5 goes into 40 8 times. Look at how close these numbers are getting to each other. There's only 6 and 7 in between 5 and 8 here. Does 6 go into 40? Well, I know it doesn't, and neither does 7. So I know I've found all of the factors of 40. Let's look at one more together. I know there's a rectangle out there that has an area of 50 centimeters squared. Again, let's start with our smallest factor. 1 goes into 50 times. 1 times 50 is 50. 2 times 25 is 50. Does 3 go into 50? I know it doesn't. What about 4? Can 4 go into 50? No. What about 5? 5 goes into 50 10 times. Does 6? Nope. 7? No again. 8 and 9 don't. So in this case, I've already found all of the factors of 50. Here are my side measures of a rectangle with an area of 50 square centimeters. I found them all. There are 3 of them in this case. So now I can do 2 things. I can take a rectangle with given side lengths. Let's say this is 2 and 10 centimeters. And I know that by multiplying these two together, 2 times 10, it would give me the area. And I could say that the inside space is equal to 20 centimeters squared. Well, I could do something else now. I could say, well, there's an area of a rectangle that is 16 centimeters squared. And I could tell you, well, there's several rectangles you could make that might have that area. It could have a side length of 1 by 16 centimeters. It could be 2 by 8 centimeters. Is there anything else? Well, yeah, it could be 4 by 4 centimeters. Each of these would have areas of 16 centimeters squared. So we can start with our sides to find our area, or we can start with the area and find the factors to tell us what the side dimensions are. Okay, In our next video, we're going to look at comparing the two things that we've looked at so far. We're going to compare perimeter and area, and we're going to look at the relationship between those two. So tune in next time for that. But as of now, you should be able to do both of these things. Can you calculate the area of squares and rectangles? And can you find the possible side lengths for a rectangle of a given area? Join me next time where we go further with our exploration of measurement and polygons.